Hi, this is Matt from Gimbal Labs, and today we're talking about the extended UTXO model. The purpose of this video is to share my learning journey, and as I do my research, I'm always trying to tie things back to what we're doing over at Gimbal Labs. At Gimbal Labs, we have this initiative where we want to create an event ticketing system on top of the Cardano blockchain. We have people thinking about infrastructure, creating libraries, and user experience models. But I want to contribute by researching the extended UTXO model because that's the basis from which smart contracts are going to extend from on Cardano. While consensus protocols do the job of securing the network, it's the ledger or the accounting model that is going to prove ownership of tokens on the Cardano blockchain. In this video, we're going to cover the mechanisms and data structures of Bitcoin's UTXO model, and then we're also going to walk through how Cardano has expanded on this model to include the features necessary for smart contracts, the expressiveness of smart contracts. Okay folks, so Bitcoin's UTXO model can be represented by a graph. And a graph is just a set of nodes related to each other via a set of edges. And we see here that the node is just these purple circles, and each node is actually a transaction on the blockchain. And then each edge are these arrows, and you can see these lines with arrows that they have a direction. That's going to be very important in a few minutes. So each of these transactions are related to each other, and the direction of these arrows kind of tells us how they're related. All right. So next we're going to move away from this 10,000 foot view of the UTXO model, and we're going to dive deeper into how it actually looks like, how the guts of it look like. All right, so here we are zoomed into our 10,000 foot model, and just imagine that the previous transaction is one purple circle, and the subsequent transaction is another purple circle. And we're going to go talk about what's inside of these transactions. Each transaction has a set of inputs and a list of outputs. And whenever you hear that a UTXO gets spent or consumed, what's happening is that the unspent transaction outputs from a previous transaction get consumed by a subsequent transaction. So the outputs of the previous transaction become the inputs of the new transaction. And you can see here that the outputs and inputs are balanced. Okay, so now we understand how each transaction in the UTXO model is related to another. Namely, to reiterate, the outputs of a previous transaction become the inputs of the subsequent transaction. But now a question arises, and that is, who can spend these UTXOs? Who can spend these unspent transaction outputs? We don't want just anybody to be able to spend them, because that would be equivalent to someone reaching into your wallet and taking out your $5 bill. We don't want that happening on the blockchain. So the UTXO model has this concept of a validator function that gets attached to each output of a transaction. And what happens is when you on the blockchain try to spend a UTXO, you pass this parameter called a redeemer object to the validator function. And without going into depth about what the redeemer object is, the validator function returns true or false, and if it's true, you get to spend the output, and if it's false, then you don't get to spend the output. And that's kind of the security model. Pretty simple. So that's pretty much it. That's Bitcoin UTXO in a nutshell, without going into too much detail, that is. But we can see already that we didn't talk about smart contracts, we didn't talk about expressiveness in this model. And that's because the validator function is limited. You cannot pass your own logic to it or anything like that. Its only job is to maintain value in the ledger and to make sure that the right wallets have the right permissions to spend the right outputs. So Cardano extends the original UTXO model, and by doing so it provides increased expressiveness and it enables smart contracts. And we do this by upgrading the validator function to take in 2 additional parameters, and we'll talk more about those parameters very soon. And we do all this while preserving the data flow properties of Bitcoin's UTXO graph. That is, we forgo shared immutable state, which we know and has discussed how this creates problems in other smart contract platforms. The innovation in the end is the support of implementation of constraint emitting machines, which is just a specialized type of state machine via smart contracts built using Plutus Core, or in the future any programming language you choose. Okay, so here we have an example of a smart contract represented by a state machine. And to give some context, we're looking here at a multi-sig contract, smart contract. And a multi-signature contract is when a group of people, they lock down a certain amount of value, a certain amount of cryptocurrency value in this case. And they say that, let's say that there's 5 people entering in this contract. Well, you can make a multi-sig contract that requires, for example, 3 out of 5 signatures from the 3 out of 5 people in order to release some of that value from the contract. So here we're looking at a state machine that represents this contract, and we see that it looks just like a graph. It is a graph. And in this case, the nodes represent states and the edges represent transitions between state. And here we have, looks like we have 2 states, the holding state and the collection state. And you can see that we can move from the holding state to the collection state by proposing something. So you'll propose that we release a certain amount of value to an address K within D blocks of an epoch, right? And once you do that, we enter the collection state. And at this point, we can go, there's multiple transitions that can occur. So we can see on the right side, we have the add sig transition. So as we can see, when we propose, we created a new set of signatures, and people in the contract might get notified, hey, do you approve of this transaction? And if you do, you can add a signature to the set of signatures. And this, while we're in the collection period, we're in it for D blocks of an epoch and an interval of D blocks, and we wait and we see that within that period, if we have the agreed upon 3 signatures or more, then we can then transition from the collection state to the holding state by doing a pay transition. So you see that here we have the if signatures are greater than 3n, then we pay out that value. Or if we reach the end of the block intervals of the proposal, then we just cancel. So now the question becomes, how do we represent this state machine on the blockchain? Well, the idea is that we can regard the individual transactions in a continuous chain of transactions as individual steps in the evolution or the life cycle of a state machine. Now we have an idea about how a state machine can be represented in UTXO. But now another question arises, and that is, how do we maintain valid state across transactions? Well, this is where that new parameter for the validator function comes in. In the original validator function, there was only the redeemer object as a parameter. But now we are adding a new parameter that we will call datum, where datum is an object that contains the state of the smart contract. For our multi-sig contract, the state is extremely simple. It's just either holding or collecting. So now let's look at the guts of how a transaction on the extended UTXO model might look like. We have a set of inputs and a list of outputs, just as before. Only now they come with some extra data attached to them. The validator function is no longer attached to the output. Instead, the output consists of a value, address, and a datum hash, which is just a hash of our datum object. And now the input will include a reference to the output we are trying to consume, the validator function, the datum object itself, and the redeemer. Now let's walk through how we validate an input in a transaction. For each input in a transaction, we will look up the output we are trying to consume. We see that our multi-sig contract is holding 500 ADA at a certain address, and we also have a hash of the smart contract's previous state. We must inspect the previous state and determine whether the consuming transaction is making a valid change. We see that we were previously in the holding state, and the consuming input is trying to reach the collect state via a proposed transition. And from our animation, we see that this is indeed a valid transition, and we will be adding a new empty set of signatures to our state. But that is not all we want to validate. Since we have an empty set of signatures, we want to make sure that the consuming transaction is not yet trying to send that locked value in the contract to another address. And that is where the sneaky last parameter comes in. In order to make sure that the consuming transaction is not prematurely spending the value of the contract, we must also pass the consuming transaction's context to the validator function. This way we can peek into the transaction context and look at its outputs to make sure everything is legit, and we can also look at the transaction's validity interval to make sure that we are still in the valid interval in which this contract can execute. As you can see, the extended UTXO model makes it possible for us to have smart contracts and more expressiveness in the Cardano blockchain ecosystem. So that was a high-level view of how it works. And we're not going to stop there. I think this is going to become a series. Next thing I want to do is design a state machine for our event ticketing system, and then maybe try to implement it in Plutus Playground. So if you like what you saw, please like and subscribe so you can see the next video in this series. Thanks for watching.